Last time, transformers vanished in per unit. But a real transformer isn't a perfect 1-to-n box. So what got left behind? Its own impedance. Push current through a transformer and its output voltage sags. Short its terminals, and something inside holds the current back. That something is the transformer impedance, hiding in the windings. So how big is it? And how do we model it and drop it into our per-unit network? Let's open it up. Here's what's really inside. Start with an ideal transformer. Just the turns ratio, 1-to-n, no losses at all. But the windings are made of copper, and copper has resistance. So add a small series resistor, R. And not all the magnetic flux links both coils. Some of it leaks. That leakage behaves like a series inductor, a reactance, X. Put them together and a real transformer is an ideal transformer in series with a leakage impedance, R plus JX. In power systems, X is much larger than R, so we often just call it JX. There is also a tiny branch that magnetizes the core off to the side, but it's so small we usually ignore it. So the model is simple, an ideal ratio plus one series impedance. Now drop it into per unit. Remember the trick from last time. We picked the base voltages to match the turns ratio, so 1 per unit volt means rated volts on each side. Now watch the ideal transformer. It's 1-to-n, but measured in per unit, that's 1-to-1. It does nothing. It vanishes. What's left? Just the series impedance. In per unit, a transformer is 1 impedance, Z'd, and the two voltage levels merge into 1. So where do we get that impedance? Straight off the nameplate. The maker runs a short circuit test. Short one winding and slowly raise the voltage on the other until rated current flows. The voltage it takes, as a fraction of rated, is the impedance. They print it as a percent. So an 8% transformer has a per unit impedance of 0.08. The percent on the nameplate is the per unit impedance. Let's make it concrete. A transformer rated 50 MVA, 138 to 13.8 kV, with 8% impedance. Step 1. The per unit impedance is just the percent over 100, 0.08 per unit on its own 50 MVA base. Now, what is that in real ohms? It depends which side you're standing on. On the high side, the base impedance is 138 squared over 50, about 381 ohms. Times 0.08 gives about 30.5 ohms. On the low side, the base impedance is 13.8 squared over 50, about 3.8 ohms. Times 0.08 gives about 0.3 ohms. Different ohms, but the very same 0.08 per unit. That's the whole point. 1 per unit number, true on both sides. And to use it in a system on a 100 MVA base, just change the base, 0.08 times 100 over 50, 0.16 per unit. So, a transformer in per unit. A real transformer is an ideal ratio plus a leakage impedance. Go to per unit and the ratio drops out, leaving one series impedance. The percent on the nameplate is that per unit impedance, and it's the same on both sides. Change its base to match your system, and you can drop it straight into the network. Next time, the synchronous generator, and the reactance that decides what it does the instant a fault hits. Subscribe, and I'll see you in the next one.